Good morning. Firstly, I'd like to say it's very nice to be here. It's very exciting, my first time in Russia at a conference. And I'm here to explain the approach about building evolutionary architectures. One of the reasons this is really important is when you think about Agile, it's not just about process, it's also about Agile software development. And in today's age, it's really about how do you evolve software that continues to last with change as lots of different things change in the industry. I work for a German bank called N26. We're on a mission to be the first bank that you'll love. We're not out in Russia, but we really focus on sort of user experience and trying to make things as simple as possible. One of our last sort of products out of our banking products is something that we called Spaces, and it's really about an easy way for people to sort of manage money. And I understand that here in Russia, it's actually a pretty good banking experience. So I'm not sure if we're coming to Russia anytime soon, but our hope is to make banking as easy as possible. And we're applying a lot of the principles that I've talked about today about building evolutionary architectures. We deploy more than 120 times per week, which is maybe unusual for a lot of banks, at least in Europe. I'm not sure what it's like here. And one of the reasons that we do this is to think about how do we evolve systems really rapidly. And this is one of the benefits that I was able to sort of work as CTO of trying to instill the culture and practices of how do you evolve systems rapidly over time. Yeah, we had a very big funding round as well last year, which was very exciting. And I'm actually moving into a role called Chief Scientist as well, which is actually focused a lot more on the technical side. I've written a lot of books, and one of them that I'll be talking about today is building evolutionary architectures. If you're interested also about technical leadership, that's a topic I'm also very passionate about that you can approach me in the breaks, and I'll be around to talk a little bit more about that. But the reason that we're here today is really to talk about evolution. And why is it that we talk about evolution? Well, one of the things that evolution teaches us is about change. And the fact that when you think about evolution and biological evolution, change is inevitable. If you want it, it'll happen. If you don't want it, it will still happen. And you will have to cope with all of that. And what's interesting for us is thinking about two types of changes. The technical side, which is often what we think about in software, but there's also the domain side, so the business side of software that you also have to think about when you think about change. And when you think about technical changes, there's a lot of things that have changed over time. I won't go into all of the details, but you can think about everything from programming languages, right? So the most recent one is probably Kotlin, but there's been Go, there's Python and Ruby, and there'll be more programming languages as we go as well. And each time that something changes in our technical landscape, we have to think about what problems do they help us solve, and how do we adapt to make the best use of those technologies to help solve business problems. Another big thing that has changed over time is really perhaps the thing about the internet. So back in the days, network was very, very expensive, and connections between servers was very, very expensive. But now we work in a very distributed and interconnected web of different applications, and that requires different ways of designing systems and services. And I'll touch upon that a little bit later. I think also open source is one of those things that have really changed the way that we build software. So when I first started working, everyone used to write their own logging framework, right? Everyone used to write their own sort of error framework, and lots of different things would be repeated again and again. Today we have a rich resource of different open source libraries and frameworks we build on top of, and we can focus a lot more on what's unique to our application and process. But technical isn't the only types of changes that we have to deal with. We also have to deal with the domain changes. And when I talk about these are the things that are the business reasons why we make changes. So these are things like revenue models. So it's very rare today that we go out and buy probably a whole album. Some of you probably use streaming, and you pay by subscription basis on a monthly basis. And that changes the way that we have to account for usage, how license and distribution of license fees get distributed to all the sort of artists. You also have to think about perhaps the the expectations from customers. So for those of you, if you remember the early days of the web, people were very tolerant of very basic web pages with maybe the blink tag. Today, we expect rich, colorful user experiences on the web, and even more so demand on mobile devices and evolving platforms as customer needs change in the business domain area as well. And of course, there are different markets that we have to sort of cater to. So probably in the fintech space, the latest one is probably blockchain, and what does this mean for lots of different distributed ledgers? And of course, that creates new products and new markets that you also have to adapt to and make sure your product adapts to. So if we accept that change is inevitable, what does that mean? What does that change about the way that we think about software? And so this was kind of the essential question that we asked in exploring this book about building evolutionary architectures. What if we architected a system for change as the first principle? How would that change the way that we build software? How would it change the way that we organize our software development ecosystem organization to be able to evolve systems for change? And so we came up with this definition of what we mean by evolutionary architecture. An evolutionary architecture supports incremental, guided change as a first principle among multiple dimensions. And in this talk, I'll explore the three main elements of this definition. The first one of them I'll talk about is about incremental. And what we mean by this is architectures are evolved through incremental releases. And in biological terms, this is really about generations, right? So reproduction from one generation to the next. Which genes are successfully propagated to the next generation? And what this means is, for us, incremental releases in software represent generations. So if you think about your software system, you start off with some sort of initial version of that system, and then you want to make some changes to it. But you don't really know how the market will change or what tools will be successful, and so you may end up with a few variants. And over time, you may end up with a very different system than what you originally planned, just through evolving and responding to the change in the environment. And what this means for us is that your ability to sort of release or go through a next generation is one of the things that gives you the ability to evolve your systems. And the question you should ask yourself is, how long is this? How fast is your ability to actually release your system and create a new generation of software? And so when we think about generations, you can think about this in another term called cycle time. And cycle time is this idea about time taken to get a simple change all the way into production. So from idea to implementation and into use by people. And what's really key about this is that you have to be able to do this repeatably and reliably. So as a startup, of course, you can kind of keep pushing changes into production, but at some point things start breaking, and you need to be able to do this in a way that's sustainable. Now, what's interesting about this is that this concept isn't new. These are actually a lot of the concepts from continuous delivery. So we see the basis of continuous delivery as a foundation stone for building evolutionary architectures. But continuous delivery isn't enough. And this is actually where the DevOps movement comes in. So not only do you need the practices to be able to build software in a continuous delivery pipeline, you also then need to get it over that last production mile into the hands of users. And often this is about getting developers and operations to work really well together and to bridge the two worlds, which is DevOps. So I definitely recommend the Phoenix project and also the DevOps handbook about practices that will help you get all of these practices to evolve systems very successfully. So to give you a sort of simple example of these, here are a lot of practices that we see as cornerstone practices for building evolutionary architectures. So, organizations that use continuous integration, focusing on automating everything, which often means putting things under source control so you can repeat things. So anytime that you look for manual processes or checklists, it's often things that will slow down, that won't be repeatable and won't be reliable. And one of the keys is really about this improving continuously. So if you think about architecture, we often think about this sort of process of architecting. We think about what we want to build. developing, and then also releasing that change. But before we do that, we probably need to talk about what is exactly architecture. We don't have a common industry definition of what this means. So Martin Fowler talks about software architecture are the decisions which are both important and hard to change. It's interesting here because if it's not so hard to change, it stops being an architecture decision and starts becoming a design decision, which is interesting. Simon Brown talks about architecture is about understanding what you need to build, creating a vision for building it, and making the appropriate design decisions. So once again, something explicitly about making decisions, but also understanding what you're optimizing for. I particularly like this quote here. Architecture are the decisions that you wish you could get right early in a project. And this is very true about software. We learn as we build and evolve and design systems, because we can't predict exactly what the environment will be like as our system evolves as well. And so when we think about this process of architecting, developing, and releasing, we often think, well, here is where we do the really important decisions on architecting. And then developing, well, that's just the implementation details. This is the really easy stuff. And then over in releasing, we think, oh yeah, this is really, really easy. All of you who've been working with software systems will know this isn't very true from experience. Instead, what we find is what appears to be important during the architectural phase actually isn't so important when we find out we throw that into production. And then actually developing a system is that we discover a lot more about the problem space, and then we find out a lot of assumptions are invariably false. And then releasing, wow, the first time was really easy, but doing this continuously gets really, really hard, and particularly working with a different part of an organization can be really painful of getting things over that line. And so what's interesting about this process, it's a very linear process. And this is where we ask you to really think about changing this and starting to think about not just the linear process of architecting, but it's a learning process of not just releasing, but also looking at how your release went. How easy was it to make that change? Was it successful? And then thinking about how does it actually change your architecture decisions the next time. And once again, what's interesting about this loop is a question about how big is this loop for your systems that you're working with. The smaller that you can actually bring it in, the less difficult it is to undo a decision. And this is really interesting because things stop becoming an architecturally significant decision and maybe just become a design decision that you could maybe test and then undo if this is quick enough. And so here, we are saying that cycle time is actually your constraint to being able to evolve your architecture. And if you want to get speed in making better decisions, you want to focus on reducing that cycle time for your continuous delivery pipeline and your release process. So that's what we meant by exploring the first term of incremental. What do we mean by guided change? So what we talk about in evolutionary architecture is systems are sort of guided through evolution with fitness functions. For those of you that have done machine learning, this isn't a new concept. So for those of you who haven't, a fitness function is an objective function that measures how close a given solution fits to a particular goal. This means you don't focus on how a solution is found, you focus on what does a good solution look like, and then people sort of test for the data. And this is exactly the same approach we talk about evolving a system. You spend less time focusing on how something is done, and you focus on what is important as a characteristic that you want in the systems that you're building. Tangibly, what this means is you need to think about what are important characteristics for your system, and what are the things that are not so important. And every system will be different. So if you're building a content management system, that will have different characteristics than building a payment gateway. And so you need to go through a process of identifying what are these things. And classically, these things are sometimes called non-functional requirements, cross-functional requirements because they cut across the entire system, and you're not ever done the first time you do it, but you have to do it through every feature that you build, and sometimes called system quality attributes. And this is what we encourage you to really explicitly think about and model and make decisions around what is important for the system that you have. Now, once you actually identify and articulate what are those characteristics you care about, then the question is, how do you make sure that these things become objective? And so this is really the question about, in software, we've found 3 ways that people can make this happen. And these are about metrics, tests, and processes. So things to make sure that these quality attributes are built into that system and revisited explicitly. I'll give you some examples as well. So we'll talk about atomic fitness functions, we'll talk about holistic, and we'll talk about a continuous fitness function as well. So an atomic fitness function is testing a single characteristic. In this example, here is a fitness function that says we don't want cyclic dependencies. So we know from change, it's very hard if a system has cyclic dependencies because you end up sort of untwining these changes. And so you can actually write a simple unit test. In this case, it's using an open source library called jdepend to enforce that you don't have cyclic dependencies. And it's as simple as adding this into your build to make sure that nobody ever ends up adding cyclic dependencies. If you want to be a lot more explicit about how you layer your packages as well, you can do that as well with jdepend. So in this example, we have a web depending on the utility package, a repository depending on a utility package, and the web depending on a repository. And if you end up with unwanted sort of dependencies, then this test will actually automatically fail. And so this is a way that you can actually enforce programmatically and automatically a fitness function on how you want to structure your code base, so add modularization. Java 9 actually does this a lot more explicitly through modules and the dependencies that you can actually define through this package. But the question is, you don't need to have a process or a person going around asking and auditing. You can actually automate this process and give that feedback to engineers much, much earlier as well. I want to talk about a little bit about the holistic fitness function. So when I was consulting, we were working for a particular company, and they had an interesting performance problem. And so we actually came in to re-architect a system to help them deal with a system that required a lot of input of small files very rapidly. So we built the system, and one of the characteristics we obviously determined was important was performance, so both throughput and latency. And so what we ended up sort of doing was deciding, okay, this is important as a characteristic for the system. How do we make sure we never ever sort of fail upon that characteristic? So performance was extremely critical. What we ended up doing was building a continuous delivery pipeline of performance tests. So as we made changes to the system, then we would be able to have confidence that these performance tests testing characteristics like throughput, latency, and different profiles of load would work very well. We ended up building a sanity performance test because this is often something to give you fast feedback about how you build your performance tests. And then we did things like a memory soak test, right? So running a profile with high volume for a long time to make sure things worked, and also an escalating load. Now, what was interesting was one weekend, we came back and looked at some test results and found, there's some really unusual behavior in our tests. So if you ever do performance testing, a pro tip is to make sure you actually graph these things, because then you can actually see interesting bits of behavior. And one of the interesting bits of behavior we detected was, as we were running a sort of performance test, we started to notice there was a peak in latency. And in our graphs, we could actually see this peak happening on every hour. We're like, we haven't changed that much in the code base. What could have actually caused that? So we did as we normally do. We rolled back our code changes to the time where we thought that there was no problems. We ran the tests again, and we still got this peak in our sort of performance tests. And we tried to find out what was going on, and then we ended up talking to some of our sort of systems engineers responsible for the environment of where we were running performance tests. And what was really interesting was there was actually a misconfigured disk controller that would actually swap storage networks every hour. And it was through our performance tests that we actually discovered a misconfigured disk controller, and that was actually feedback we could give to the systems engineers about ensuring that never happened in production. And so this was an interesting thing that you wouldn't have picked up in the software testing, but is a holistic thing because you're testing your system as it would be in production. And so once again, this is thinking about what are the characteristics you care about and making sure you implement them. Now, something that's a continuous fitness function, as a really good example, is Netflix Simian Army, right? So for them, reliability is really key. And what they have is this thing called the Simian Army, which is a whole bunch of different tools called chaos monkeys that break things, right? So they're turning off networks, they're slowing down network connections, they're sort of killing random processes to see how resilient the system is. And one of the really great testaments to them was that actually when Amazon's S3 went down, I think it was now 2 years ago, they were the only company that was not affected. Even Amazon themselves were affected, with images not appearing on their shopping carts and things like this. And so for them, they said, actually, resiliency is such an important characteristic, we're going to invest in automating this and building it in to make sure that we build that characteristic into the system that we're thinking about. So there are examples of some fitness functions. And a good saying here is if it hurts, do it more often. Not because we like pain, but because it's feedback. If it hurts, hopefully you actually respond and you improve the system to get better at it. And that's the whole point of these fitness functions, is it doesn't really help to have a person come along and sort of tell people to do this. Automate that process, give that feedback early, and improve the system. So there are known knowns, and there are also the known unknowns that we know about, but there are also known unknowns. And so one of the careful things here to think about is not over-engineering change, but really just being able to respond to what you think is going to actually change given the known horizon. So as an example, we can see the evolution of in-house data centers to things like cloud computing. And the next stage that we're seeing is definitely about serverless. But it doesn't really matter to think about what's beyond serverless yet until we start to see that actually the market's going in that direction. So don't try to over-engineer. So we looked at incremental guided. Let's look at multiple dimensions. And what do we mean by this? Well, so there are technical changes that I talked about. So libraries, tools, frameworks, and platforms that you need to remove or add or upgrade. And then there are domain changes, and these are often the ones that we often always get asked for. So new features, a tweak to an existing business flow, pricing change. And so let's have a look at some architectural approaches about how well they support changes. So we'll look at 4 different architectural patterns and see how well they actually support change. So the first one, which I hope you don't have, is the unstructured monolith. This is actually from a previous client of ours. So if you model this as a dependency graph of a class calling another class, you can actually see the length of the line, the thickness of the line is how many calls there are. And in a well-structured monolith, you'd start to see clusters around this, and these would represent the modules. But obviously, in this kind of case, if you try to make a change, say upgrade a logging framework, you probably have to go through the entire code base to work out what needs to actually happen, right? If you try to make a pricing tweak, you probably need to go through and understand what impact will that pricing tweak have on everything else in the system. So it makes it very hard to make changes at both a technical perspective as well as a domain perspective. So this is actually something that doesn't support evolution very well. There's layered architectures, and these are things like Spring MVC or Spring Boot, and then Ruby on Rails. And these are where you have very explicit layerings between different things, popularized, I guess, by the web. And these are kind of typical layers that you might have. Now, if you need to upgrade a database framework, for instance, or Hibernate, where do you go? That's pretty clear. You go to the persistence layer. So it's very optimized for replacing technical layering. But what happens if you need to make a business domain change? So what happens if you add a new customer field to a screen, and then you have to persist it throughout the entire stack? Well, you have to then make a change to every single layer all the way down, even though there may not be any business rules. And so you actually might need to do more work in order to support change. And there are 2 trade-offs that you can actually make in this process. You can actually be consistent and make that change to every layer, copy from one object to a data object that then gets persisted, or you can choose for inconsistency and say, actually, there is no business rules, so we can just skip a layer. And that doesn't make it easy or wrong, it's just a choice about how you make your systems. So another architectural pattern is called microkernel. So Maven is a microkernel architecture, Eclipse, and Firefox. And the idea with a microkernel architecture is that you have a core engine that has pluggable interfaces, so you can add in extra different areas. Now, what's interesting about this is you can make some technical changes depending on the plugin. So if you use Eclipse, for instance, it's very pluggable with what you can actually do with that. But also you can add new features through the plugin interface. But what's really interesting about microkernels is that you can't change that core engine. So if you ever try to make Firefox not look like a web browser, it's going to be really, really hard. And so this kind of architectural pattern can support technical and domain changes, but you have to be really confident that your domain matches exactly how that microkernel is designed to work. So for those of you who've used applications built on top of Eclipse, you can all tell it was built up on top of Eclipse framework because of how it looks, right? You'll never change the fact of that. And so this is where it's a question about, is this actually what you want? And is that a big bet for your domain? And this brings us to, I guess, the latest exciting architecture pattern, microservices. And I talk about this about microservices done well. So this is really about the domain-based services focused on a particular area and making sure that there's loose coupling between them. Now, what's really interesting about this is that if you say, okay, well, let's upgrade a technical library. So let's change the way that we maybe manage our customer information. We want to have a graph database of how customers are related. Well, we know this is one service that we have to go to, and this is one layer in that service that we have to make the change. And then we don't have to touch anything else. We can make that change relatively easy. What happens if we want to change the way that we actually process our inventory? So what happens if we want to change the way that we manage our inventory catalog? Then we know this is exactly the service that we have to go to make that change. So it supports both technical and business changes. What's the trade-off? There's always a trade-off. Well, the biggest trade-off here is you end up with a much more complex landscape. So for a single team that has to manage this ecosystem across a set of services, it's quite complex perhaps, because then you have inconsistencies across the entire set of services. And that's one of the trade-offs that you have with microservices. If you end up with a lot of distribution as well, of course you also have distributed contention, which will affect reliability as well. So we've looked at incremental, guided, and multiple dimensions. Let's talk about a little bit about some of the practices that we have. So who knows about Conway's Law? Okay. So Conway's Law talks about how the communication structures of your organization will be reflected in the architectures that you want. And so an interesting thing about this is thinking about how do you inverse this? And if you want a certain architecture, how do you structure your teams to get that architecture that you care about? So in a typical layered organization, you often end up with a layered architecture by choice. So groups of working in different areas. But if you really want to have a different type of architecture, you actually need to think about how you architect your organization. So if you want to move to, say, microservices, having different departments or functions working in silos will be really hard. I think my clicker's died. Oh no, there we go. And so this is actually where you want to perhaps regroup your people to be working in microservice-based architectures with fast feedback loops. And this is what we call inverse Conway's maneuver. So if you want to have a certain type of architecture, you need to explicitly think about how you design how your teams are formed and the skill sets they have to be as effective as they can be. And what you'll end up with is often sort of loosely coupled but highly cohesive teams who own a product area if this is the architecture pattern that you want. Another sort of thing that we see with evolutionary architectures is moving away from rule-based architectures to principles. So engineers are making decisions all the time, and so what you want to have is helping them give them better context about how to make a good decision. One of the first criteria is obviously talking about what are those important characteristics about what is a good decision in the domain that you're caring about. But really move away from sort of checklists of rules and help them think about how do they make better decisions in the area that you're thinking about. Another practice that we kind of encourage people to think about is moving away from project-centric based development to product-based development. So if you think about sort of projects, you get a team together and then you start something, right? But at the end of that project, what happens to those people? Well, those people then are sort of broken off and then they go on to work on other projects. And what happens to their knowledge about a decision and the context about what happened to that decision, it often gets lost in the annals of time. And so you end up bringing together more people who then say, why did they make this crazy decision? We'll now make the change that we think is right. And then they continue on and so on and so on. So you end up with multiple generations of different decisions, sort of with different cultures. And this is where we encourage people to really think about, if you want to evolve a system, then you actually want to think about sort of the product-based approach as well, right? So thinking about Amazon's you build it and run it kind of approach, thinking about how do you evolve that system, because when you actually deploy changes and you make a decision that was maybe bad to monitor or bad to operate, you'll make a better decision next time because you'll be the people who'll be woken up. So it's about closing feedback loops and making sure people have the right impact and feedback. One of the things you hear about is about this idea about last responsible moment. So if you think about external dependencies, those external dependencies are going to change over time. And so those are things you have to be really careful about externalizing and keeping on the edge of your systems as much as possible. So if you think about some external dependency, it could be a product that you integrate with, a service or a library, then you want to start thinking about what happens if you make that change in multiple places, right? So how many times do you have to make that change, and how do you make that change easier? And this is actually what happens when you start to think about the adapter pattern. And this leads on to the ports and adapters pattern that Alistair Coburn talks about. So you have some external library dependency, you have your internal representation of that, such that if you ever have to change that externality, you only have one place to change that, and everyone else is protected from that change. So you make that change easier and simpler to make. So this leads on to the ports and adapters problem. Another approach is thinking about like a town planner. So really thinking about not making decisions for people, but your role is really about helping people make better decisions, so not making the decisions for them. So a town planner is not going to every house and saying, here is how you have to build it. They actually talk about, here are the general zones, here's the principles of how you work, and then you have to make choices as a house builder to make sure you comply to those sort of decisions and things. So avoid making decisions for people. Another tool is architectural briefings, and this is really about getting people to share the reasons why they make discussions. And so this is really about getting somebody to talk about what's the history and decision behind things, and making sure that people have the right sort of discussion around that. And what's interesting about this is that anybody in a team, not just somebody called a software architect, can talk to people about why they make decisions, right? And so what's interesting about this process is also making sure that you get things out of people's heads, where people can have different mental constructs onto something like a whiteboard, to make sure that then you can actually see the differences, and then you can actually talk about how do those differences evolve according to what you kind of need, and then make sure that people have the same mental model at the end of that. And in this process, what's interesting is that everyone becomes an architect, right? So there's less of a blur between one architect and engineers, but actually people making architecturally significant decisions, and that can be anyone. So we've talked about a lot of different changes, and I want to sort of quickly summarize with a couple of different anti-patterns, traps that we kind of talk about. The first one that I want to talk about is the last 10% trap. So some of you may remember the generation of 4GLs, right? Models that can program for people. And one of the reasons that sort of didn't work is that you hit an abstraction layer. And at some point, you do everything that the tool was designed to do, and then somebody wants something that that tool was never designed to do. You make some workarounds, you can get to that extra 90%, but then that last 10% you will never ever get to because you've run out of workarounds, you've run out of hacks that the tool was never designed to do. And this is why 3GLs are best suited if you think about adapting for change. Another thing to be very careful about is coding via configuration. So if you are actually making choices like if statements and loops, just use a proper programming language rather than using some XML or JSON configuration tool. You also want to be careful about product customization. Sorry, I skipped over that. And product customization is one of those things where if you choose something, don't try to customize it too much because you'll often end up behind the evolution of that product and on some branch that will be hard to evolve over time. Now, with evolutionary architecture, I sort of want to close by talking about when it's applicable, and it's not applicable over everything. Now, when we think about software, we often think on a sort of build versus buy sort of spectrum. And rather than what we think about, we often think about functionality, right? So we buy because it'll give us lots of things, or we build, but we have to do a lot of code in order to actually make things work. And one of the things you should really think about is how much is it going to be able to change over time? And so custom code, you'll always be able to change to how you would like it in your domain. But if you're relying on some components off the shelf or software product, you'll always have to negotiate with a vendor to actually get that change done. And so you'll have to think about what's right for the area of software that you're working in. Now, to sort of think about this, is you can think about systems in terms of value generating or the need for rapid change. So there are some systems, for instance, that are probably the things that you're not going to change a lot. So commodity. So nobody here should probably be building an email system because that's not your product, right? So you just use something off the shelf. Sometimes there are support things like Jira or ticketing systems that you need some custom workflow, but once it's established, you don't need to make lots of changes to that. There are some systems which are going to be highly changeable, highly valuable potentially, but if they fail as an experiment, you may never need to evolve them. So prototypes are a really good example of that. And what we posit is actually there are systems that are really value generating, so they're key business revenue generators for your business that need to keep evolving as your business evolves. And this is actually where you would really care about the systems for building evolutionary architectures. So this is where you would apply a lot of the practices and techniques that we talk about by thinking about what are those systems in your ecosystem that are strategic systems that will need to make change over time. So to conclude, I hope you've understood that an evolutionary architecture supports incremental, guided change as a first principle among multiple dimensions. And what's interesting about this, it's not just a technical system, but it's something about architectural choices. It's also about the decision-making process and thinking, so the environment in which you work in. And it's also about the organizational and cultural aspects of how people are working together to build systems that evolve, or maybe don't evolve as quickly as much as you'd like. So thank you very much. My name's Patrick Hua, and this was about building evolutionary architectures.
Thank you. So, если у вас есть вопросы, пожалуйста, поднимите. Oh.
Patrick, hello, my name is Sergey, and thank you for the impressive presentation. And my question is, in your practice, what is the biggest challenge you faced with the transition to evolutionary architecture, and how was this problem solved?
So the biggest challenge for me for transitioning to evolutionary architectures is often about getting people to change their mindset from thinking in terms of big change to thinking about reversible decisions. And so there's a lot of things about being able to ask people, how easy is it to undo a decision? And this is where things like release cycles will dictate that. So when I've consulted for existing organizations like other banks, you know, they think in terms of 6 months or 12-month release cycles, and that's really hard to undo change. And so the first thing is then working with them to reduce that down, so then the idea of the cost of undoing a decision is very easy to do. But I think for me, it's really about this mindset, right? So how do you get people to sort of start thinking about multiple options and then the reversibility of decisions rather than actually some of the technical practices? Good question.
Еще вопросы? Okay, so I'll be asking a question as well. So, what may be the first step to get to, to evolutionary architecture from traditional one? First step.
So I'll give the typical consultant answer here. It depends. I think there's a couple of different things you can do if you want to adopt evolutionary architectures. So one of them is think about explicitly modeling those characteristics you care about, those fitness functions. So I think in the big sort of world of agile, sometimes explicit architectural and modeling and discussions get lost in that process. So if you look at the Scrum Guide or XP, they never explicitly say you should do some architectural modeling and here's how you do it. It's still important, but I would say that's where you would start from a practice perspective. So talk about those system quality attributes, think about what is important and how to quantify them. And then the other side is if you're sort of working in a more established organization, then you should work on both continuous delivery practices and the DevOps practices. So speed up the ability to release changes into production and also then to undo changes if possible.
Thank you. Еще вопросы?
Hello.
Oh, there's one more.
Thank you, guys. First of all, thank you for the good presentation. It was quite interesting. The question is the following. Maybe you know that in the field of, let's say, real architecture of buildings, there's also some approach for dealing with changes and even the approach to treat some layers of change. Different parts of the buildings change with different speed. So do you think that for the system architecture, for application architecture, some similar approach is possible? And which types of layers, can we define some similar type of layers with different speed of change? What is your vision?
It's a great question. I'm not so familiar with real building architecture and how they cope with different types of change. But I think there is some truth in that, which I'm guessing is your base foundation of how you build the system originally will make it easier or harder to change. And so this is some of the things where if you're building a strategic system that will need to evolve, and you start that off by building it on top of somebody else's product that is owned by somebody else, that will ultimately be very difficult to change because it'll be dictated by that other company or the product direction of that other company. And so this is where I would say some of the foundation of how you support change is a good decision, right? So if you're going to make a strategic system, don't build it on somebody else's product, but really think about how do you keep it decoupled and separate from that external product as much as possible. So how do you reuse some of their features, but not necessarily build on top of their product and be dependent on that? And some of the practices I talked about, like the ports and adapters, are a really great way of externalizing those dependencies. So making sure that those things are kept outside of the boundary, and you keep everything that's in your domain to the core center of your application, because that's the proprietary business knowledge that is unique to your business. And so you should really own that and not outsource that to another company. So, good question.
Hi, I have a question. Evolution can kill generation that unstable. But in business, in our architecture, in code, we can't kill some components because full system will down. How we can solve this concern?
It's a really great question, and this is one of the reasons why people invest in things like A/B testing frameworks. So one of the reasons you want to go down this approach is so you have to ask yourself, how do you architect a system such that you might end up with two implementations of something? And one of them is probably going to be better than the other one, and you'll want to be able to easily swap them out. And so that's part of the art of, I guess, designing and architecting a system for that, is that will depend on the business that you're in, and there are some technical approaches of how you can do this very easily. So in microservices, it's very easy to, say, run parallel instances of two services because you can redirect traffic through something like a load balancer. If you're working with a complete monolith and you have to sort of swap out two modules, that's a lot harder, for instance, right? So this is one of the reasons why things like microservices are really popular, is that you can actually test multiple implementations out and then easily undo some of that. But I think part of it is then thinking about how do you do things like running multiple implementations and then choosing a better approach. What is a lot harder, I'll admit, is that once a user is using a particular feature, it can be hard to convince the business to maybe kill that feature because only 2% of your users use this thing, and there's a big maintenance cost. And this is where you have to come up with, I guess, the business case of saying, here's how much effort we use as an engineering team to maintain this. Does that make sense to actually evolve in that product longer term?
So, another one.
You said you're chief scientist right now, but your Twitter profile says you former CDO of a company, right? There's a question, how did you, well, maybe it's not a correct term, but enforce this architecture style for the company? How did you check with teams and people in the company about that?
So I don't think with any of these things you can really enforce some of these practices. So for me, it's about building a culture of awareness around this. My approach is that everyone who builds software are highly intelligent people who know how to learn and know how to solve problems. Like, that's a fundamental of how engineers kind of work. And telling people how to solve problems is not really exactly how people come into software. And so what we want to do is talk about, what is a good decision in the field that we're in, and how do you know you're making a good decision according to the environment that you're in? So for a bank, for instance, obviously security is really key for us, and making sure that we manage things like privacy and information like that. And so they're characteristics we ask people to consider when they make decisions. And so what we try to do is build in feedback loops to make sure that people understand these things. So when people are designing systems early, we do threat modeling very early to sort of build that in. And then we're looking at ways of automating some of that feedback in as well. So things like library dependencies, you can actually scan automatically for vulnerabilities and give that feedback to teams immediately. But some of it is some of the process stuff that I talked about. Some of it is about automating some of the metrics and automating standards. So for instance, in a service definition, we say that a service definition has to have a good health check endpoint, and that's built into our CD pipeline. And so anybody who creates a new service, that won't ever go live until they actually have that health check endpoint as an example, and then they know they've satisfied the criteria of what makes a good system.
Thank you. So we have got out of time. You can ask your questions, face to face, yeah?
Yep, I'll be around.
After, over here.
Yeah.
Thank you. So, давайте еще раз похлопаем.
Thank you.
Thank you for coming to Moscow, for coming to Agile Days.
Thank you very much.
Great.